Hello everyone. This is today's live session that is happening on September 2, Saturday at 4 p.m. Indian time. Uh, Let me just wait for some time for others to join. Then we'll start the session. Hello. We'll be starting in some minutes. We'll start in some time.
Yeah, sure.
Okay, so we'll start with CNNs. And since this week's, uh, 1 second, let me just open uh, the Swim Central site. This week 5, right? Okay. So, so in today's week, we'll start with the CNNs and the basic concepts of CNNs. And so the way it will go is that I'll start by discussing CNNs, and then I will start by uh, doing some coding that is related to CNN, and then we'll wrap up the session. And if you have any questions, you can ping me anytime when I'm presenting, or we can have a one-on-one discussion like of some a topics. So like, okay. So starting with CNNs, yeah. Starting with CNNs, so the need for CNN starts. So we had this ANNs where the artificial neural network the artificial neural network was working fine with normal tabular data. And since we started to look at images, uh, the size of the data sort of went very high, and it exploded in the dimension wise. So to tackle that, um, like ANNs or the fully connected layers were not very memory efficient and the computationally efficient option to go. So the first thing is that the image data is very high dimensional. Second is that it is very difficult to process for a fully. It is very difficult to process for a fully connected feed for a neural network. Uh, the image. And the third question is that uh, uh, I mean, the third problem that they have is that the spatial relationship. So in the tabular data, like let's say the tabular data is data 1, data 2, data 3, data 4, and data 5. And if I pass the network in not in this sequence, if I just pass like data 3, data 4, data 2, data 1, data 5, then it's the same thing because they don't have this relationship, the spatial relationship between them in the tabular data. But in image, we cannot just pass this cat by randomly arranging the pixels around across the image, right? So we cannot do that. We just have to pass the image as it is. For this to be a cat, the pixel should be at that position that is there initially. We cannot change the pixel position of the pixel. So there is a spatial dependencies between the pixels. There is a spatial value of an image that must be preserved while processing the image. So ANN was not great at doing that. Because if you remember, so uh, one of the first way is that like uh, pass everything to this uh, to one neuron here, and then pass everything to the next neuron here. So this is one way, and another way was just to flatten it, like take the first row and create a vertical sort of pixels, then they take the second row, then arrange it below that, and sort of like that. In that way also, the image of a cat will destroy it, because if they take one row that involves its eye, the eye will be at some place and the nose will be at some other place. So it's very hard to sort of keep track of the spatial relationship with the ANNs. And the most difficult thing is the parameter explosion. There are like 2 billion parameters for just one connecting one neuron, so which is not great. And the uh, the spatial correlation is local. Like we can, I mean, it's like we need the interaction between these things. I mean, if we see a cat, it's very necessary that we see the cat as a whole. It's not like that we're just seeing a part of the cat. So to tackle all these uh, problems, the people came up with CNN, which is called convolutional neural network. Uh, what CNN do is that they sort of take a small patch of the image and look at that and look at that local region and try to gain something from it, and then they move that patch across the image to get this sort of local information from an image in a reduced way, and then they sum it all, then they sort of like, then they club it all to make a bigger image, which will have the same local representation knowledge of the bigger image, as well as the same global knowledge of the bigger image, but the size and the dimension of the image will be much smaller than the original image. It's like it's like finding an image, or like, so let's say image is a tensor. So it's like finding a tensor that is much smaller than the original one, but it has captured all the important properties of the original image. Okay, so there's two primary operations in CNNs. One is convolutions, and the second one is pooling. So convolutions are the operations where we sort of take a filter, or we can call it patch, and we sort of move it across the image to get local information from that locality, from that area that the patch is covering. And pooling is sort of pulling out the maximum value or average value in some region. Like convolution is like sort of uh, taking the information by doing some operation in all of this pixel in that region, and pooling is just, finding the fittest one, finding the finest one, and just passing it on. So we'll be discussing this convolution operation and pooling operations next in details. And once we get a small enough image, then we can do this fully connected sort of thing, because as you saw here, the reason it has 2 billion parameters here is because the image that is there in the left is very big. So it's very hard to design a neural network that is uh, sort of accommodating everything, accommodating all these pixels, and uh, also maintain small memory. So it's not possible to do that. So once we do this convolution and pooling, we'll at the end we'll get a very small image which will have all those all those properties of the bigger image, and as well as it will be much smaller than the original image, and we can connect a fully connected layer to it. Okay, so the starting with the convolution operation. So the convolution operation is sort of like you take a filter. Okay, so let's say the image size is let's say the image is black and white, just two-dimensional image. So to represent an image, we can do it in various ways. Like so, an image is a RGB value. So every image has an RGB value. So so let's say if you look at one pixel, it will have some red value, some green value, and some blue value. That's RGB. So in this case, let's just consider that the image is 2D, like it's just one value, just grayscale. And so if the image is 2D, the filter that will design will also must be 2D, because we need to sort of make this filter travel across the image uh, to parse that sort of thing. And so as we do that, so the thing is that so now what we did is that we take this filter that is there. You can see the animation. So we'll put it in the first block, first 9 by 3 cross 3 block. and we'll do the convolution operation in this 3 cross 3, and we'll get one value, and we'll fill it in the first block here. And then we shift it by one place to the right, we get another value and fill the second place. And similarly, we'll go till the end in the first row, then we'll jump one floor down, and we'll do the same thing again and again till we reach the end. So there is a formula actually that describes given an input image of size, say n cross n, and the filter of size f cross f. What is the output, the resultant output that we are getting in the other side of the operation? So there's a formula. We'll discuss it later in this slide. But yeah, so this is the operation. So what happens in the operation is that let me see if it is mentioned in the next slide. No. So what happens is that, so you take the filter values, you multiply it with all those pixel values that that is like not showing here. You multiply them, then you add them. So that's it. So it's convolution. So you just take dot product for the pointwise multiplication, point to point multiplication. Then you sort of add all those 9 values. You'll get 9 values because there is the filter size is 9, and you just add everything, and then you'll get a value, and you put that value in the block in the right. That's the convolution of. So if we're thinking, if the image is of size n cross 3, that's for 3 channel, like the depth if is 3 for 3 channel, so that is red, green and blue, so the filter size will also be 3 cross 3. Now the filter size has changed now, because we'll put the filter in the entire 3 uh, uh, 3 colors, like red, green and blue, so 3 channels. And and now we'll have, instead of 9 values, we'll have 9 plus 9 plus 9, there's 27 values, and we'll add this entire 27 values. We'll get one value, and this will be filled here in the first block. And yes, so if the input image is of size like n cross 3, and your channel size is also 3 cross 3 cross 3, the result you will get will be 2D. It's not gonna be 3D because everything is added. So 3 is cancelled. Which is, yeah, I muted her. Yeah, so the filter size is 3, 3 cross 3 cross 3. The output will be a 2D one. Okay. So this is sort of like an example. So let's say the image that we have is of the size 32 cross 32 cross 3, and let the filter size is 5 cross 5 cross 3. So as I said, the filter always extend the full depth of the input volume. Like if I place this filter on top of this, it will take the entire volume here, and it will give one single value for this entire volume. So this traveling across the image, like the travel of this filter across the image, we call the convolution operation. We always say convolve the filter with the image, that is slide the image spatially, computing dot product. So we're just doing the element-wise multiplication, which is the dot product. It's good. And so it's like that. See, it's 32 cross 32 cross 3. The filter is 5 cross 5 cross 3. What we're doing is that we're multiplying all these values that is present here in the image to this filter, and we're getting one number because we're just adding them. And we're getting one number. Is the result of taking a dot product between the filter and the small 5 cross 5 cross 3 chunk of the image. You get it, right? So that is 5 cross 5 cross 3 equals to 75 dimensional dot product plus the bias. Yeah, we also have a bias term. So we just add that bias to it. So the equation is like that: W plus X, W transpose X plus P will give this number.
So I have a question here that will the parameters of all the three filters, that is for the red, green, and blue, be same, or is it possible that they could be different also?
No. So so when you call filter, it's that 5x5x3. It's not three filters. It's just one filter. The filter size is 5x5x3. So if let's say we have an image of 32 cross 32 cross 5. Okay, let's say it's not possible. I know the image size would be 3, but let's say we have 5 channels. So the filter size will be 5x5x5. So the filter is 5x5x3. So the value that we'll be getting will be a tensor of 5x5x3. And the question about will the value be same? No. So these are the parameters of the CNN, the W's, and the filter is the parameter. We can call it W as well. So all these values gonna be different because we'll first. So this is gonna be the weights. So we'll first randomly initialize the filters, and then we'll sort of update these filters to get the optimal filter which will be learned by the backpropagation.
So
Yeah.
actually, it is not clear. Say if we are having a single filter having 3 channels, and so clearly, so how many parameters would be there? So since there is a
27.
single filter, so it would be having 5 into 5. So 25 number of the parameters, and these 25 values will get multiplied to the 75 values. It is true that because in the image we would be having the different values corresponding to R, G, and then B. But can we
Yeah.
have, I mean, can we have the different values for the individual channel of a single filter whose dimension is 5x5?
Yeah.
I
I
mean,
mean,
when I use the term single filter, I mean to say a filter having 3 channels.
no, the value. So no, there is no 25 values. So the filter size is 5x5x3. So there are 75 values getting multiplied with 75 values from the image.
Right, but then yes, it is true that the 75, but my probably my current understanding is that the
Let me see.
25 values of the filter are getting uh, multiplied to the 25, 25, and 25.
No, no, no,
75,
no, no.
no.
See, so there is in the filter, there is a total of 75 values, not 25 values. So I'll just start from the beginning. Let's say the image is now 32 cross 32 cross 1, just one dimensional image, grayscale image. Okay.
For
And
for
the
for the
filters,
grayscale, for the grayscale, it is fine. But then
yeah, the
when
for
it comes to the 3 different channels, then I mean, doubt is there. Doubt is related to the, I mean, presence
color.
of the multiple
Okay.
channels. Yeah.
Okay. So now we have 32 cross 32 cross 1 in the grayscale, and the filter size is 5 cross 5 cross 1, right? And we can just directly dot product, like, the 5 plus 5 into that small chunk of the image, 5 plus 5. There is 25 getting multiplied with 25 numbers, right? And
Mm-hmm.
now, let's say we add 2 more channels to the image, okay, and 2 more channels to the filter, okay. So now this
In case you are
the
writing something, the slides are not getting changed.
Yeah, I'm not writing actually. So actually,
Okay.
I have a like this tablet and pen, but I left that in my lab, so I just have to use the slide. So what I do is that I have actually a notebook, so where I can where I just write things because it's easier to get in that way. But unfortunately,
Okay.
I left that in
All
the lab, so I couldn't.
all right.
Yeah.
All right. All right. No, no, no issues. No issues.
Okay, so like so like there are like 3 channels now in an image, so it's just grew from 1 to 3. So the values that you see in channel number 1 is not the same that the value you see in the channel number 2. again, it is not the same with the value that you see in the channel number 3. So if you pick a small chunk, you'll get 75 different values. Not necessarily like two values can be same, but let's say 75 different values, independent values. Okay. And if
75,
you
yeah, I have a doubt here. 75 independent values of the image or the
image,
75 independent values of the filter?
see, in an image, you'll get 75 different values.
That's true.
Since now you have increased the filter size as well. Now you have added two more filter layer. Now earlier you had like 5 plus 5. Now the filter size is 5 plus 5 plus 3. This two new layer is not the copy of first layer. These are also completely different filters. So you can say the 5 cross 5 cross 3 filter is a combination of three different filters clubbed together to form one three-dimensional filter.
Okay. Because till now I was under the impression that even though there are three channels in the filter, and if the size of the filter is like given in this example 5 cross 5, then the values
No,
of all the
this
three channels would be same.
Yeah, no, they're different. The 5 plus 5 plus 3 filter have different values, like 25 different values, 25 different values, 25 different values clubbed together to have 75 different values. So when we learn these filters, so I'll just tell you the story of how this happened. Uh, so earlier we had filters, like if you see week 1 or week 2 videos, people are learning, sort of trying to design filters which can extract the edges, which can blur the image, or which can sharpen the image. So those are the filters, okay? And they are using that filters to get essential features from the image, okay, like vertical edges, horizontal edges, curves, and then the places where the image is round. So all these features they use to extract by smartly designing filters, which can give all these things. And they were using this uh, extracted feature for other image computer vision tasks like classification or object detection and all these things. But after the deep learning era came, so what people said that let's just, since this learning, like creating a filter is an intelligent task, let's just make all these filters as weights. Okay, let's just say that all these filters, we don't know all these filters. So since you are optimizing as a network, so what you'll do is that, so they ask the network that give me the optimal weights which will make this filter good enough for this task. So now the filters is the parameter. So we'll learn this parameter when we'll train the CNN. So now this filter is not extracting edges, or not extracting the vertical edges or horizontal edges or the curves. It's not extracting that. It might be not extracting something which you can comprehend. If we say see the so after this all this neural network is trained, if we just see the image that is that is obtained after putting this filter, the learned filter, we might not say that, okay, this is extracting edge or this is extracting horizontal edge. So we might be finding some unusual features which we haven't seen yet, which we mustn't have imagined. So, the task of deep learning is to learn these filters such that uh, the 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 task that is going to happen after this step, like all the what do you call that? All the like mm, the term for that. Um, yeah, so all these tasks that is, I mean, so the filter will be learned in a way so that all the tasks, all the downstream tasks that we're going to do, classification or object detection, can be done smoothly. So these are the filters that we're learning, and these filters are different for different channels. Okay, great. So we have these filters. So all these values are different. We convolve around it. Since we are getting one value for the 75 value, similarly, if we just get values for this entire image, we'll get a image of 28 cross 28 cross 1. So see, just to note here that the image size was of image was just a depth of 3. The filter was a depth of 3. Now the the resultant image that we are getting is a depth of 1. So there is a depth reduction. So what happens in a convolution step is that one filter give rise to one 2D image. Okay. So if the filter is like, if the image is like 32 cross 32 plus 5, and we have to get a filter of 5 cross 5 cross 5, and it will give us a, a image of 28 cross 28 cross 1. So it doesn't matter how many channels that we have, the answer will always be the answer of the depth that we get after this operation will always be 1. And we call this the activation map. And similarly, like, so this is for one filter. If we use another filter, we'll get another activation map. And similarly, if we use, let's say, 6 separate filters, so what we're doing is that we're saying that, okay, so we don't know if uh, extracting the vertical edge or horizontal edge or the curvedness or many more things that we not know as a human will help us getting better at the classification. So what we want to do is that we what they say is that just um, uh, take 6 filters and figure out which filter will work as which feature extractor, and then just give us 6 activation maps, give us 6 resultant image which we'll use for classification. So that's why, like, if we had 6 5 plus 5 plus 3 filters, we'll get 6 separate activation map, and that the size of the image will be, and we stack these up and we'll get a new image. So these are all individual image, but if we just stack this up, we'll get a new image. The image size will be 28 cross 28 cross 6. Did you get it? Like, and it's pretty straightforward. But yeah, so if you have any doubt, you can ask me now, because so this is the basic thing that need to be clear.
Yes,
In doubt.
this diagram is clear. That since we have used 6 different filters here, 6 5 plus 5 filters here. But even in this example, they have written that they have used 6 5 plus 5 filters. So
No, 5 plus 5 plus 3. They like
5 plus 5.
the
Okay.
5 plus 5 plus 3. Yeah,
Yes.
it's a typing mistake.
Yes. It's okay. It's clear.
Okay, great. Just 1 second.
So which tool is used to draw these diagrams? Any tools are available to draw the CNN, this kind of rectangles?
I guess, like, actually what happens is that we have 3 people for doing TSC for this course, 3 or 4 people. So what we did is that, like, someone will do the slide for that week and we'll all just discuss, and the next week we will do the slide. So this slide is done by my friend, so I can ask her like how she did it, but I guess that it is taken from a lecture, because this kind of, like, slides and, like, creating the slides and creating an entire lecture will take a lot of time. I don't think she have put all those efforts for this live session, but I guess if you go to draw.io, you can do similar structures there as well. So just check out draw.io. So I do for some of my stuff, and I prefer that over others. So you can just check there and uh, see, like, you can use these rectangles and keywords to draw there. Yeah. Okay. So this is the operation of convolution that gives out activation maps. And if we have like, let's say, n filters, we'll get an activation map of size n cross 28 cross 28. So we say the term convnet, it's a sequence of convolutional layers. So we had an image of 32 cross 32 cross 3. We applied 6 convolution layers. We get a 28 cross 28 cross 6. And then we applied 10 convolutional filters of size 5 cross 5 cross 6. So just note here, see, just one thing, I'll just drink some water. Yeah, so just note here, the image size is 32 cross 32 cross 3. So we're getting, so we have the filter need to be, the filter size of the filter, the depth of the filter should be equal to the depth of the image. So this two size can be anything because we're just convolve around across the image, but the depth of the filter should be same as the depth of the image because we need to travel across the image with full depth. So here it is 5 plus 5 plus 3. The result that we're getting is 28 by 28 by 6 because we have 6 filters here.
Yes, and why are we following this convolution by ReLU process, by ReLU activation function?
Yeah, so what happens is that you know that like for an image to be valid, the value should be between 0 and 255, right?
Mhm.
And like some people used to normalize the image and they'll all lie between 0 to 1. So first thing is that ReLU is a non-linearity. So if you have learned about ANN, so what happens is that we need to introduce some sort of non-linearity in an neural network. Otherwise, they will just learn a linear function. I mean, if you're classifying cat and dog, so we don't want our network to learn a linear function because the identifying cat and dog is not linear. So we need some non-linearity. That is point number one. And second thing is that the ReLU is the ReLU. If you look at ReLU function, it just max of 0 and x. That is, if the value of x is greater than 0, it will keep it as it is. If it is less than 0, it will just make it at 0. Okay. So let's say after doing the convolution operation, some negative value comes. Let's say the filter is somewhere -2 or -3, and some negative value comes. So that will make sure that that negative value do not travel further, and it will just make it 0. Because as an image, there is nothing we can represent with a negative value. We can represent something at 0, or we can represent something further in this positive domain. We cannot just represent something that is 0, sorry, less than 0. That's why value were used to squeeze those values and keep it in 0. Okay.
Okay, yeah, fine.
Yeah. And so we did that. We got the image of 28 cross 28 cross 6 because we used 6 filters. Now we have to do another layer of that because 28 cross 28 cross 6 is still a bigger image because we'll get around 784 cross 6, that is like 6,000. And real world images are not 32 cross 32. Now it's like coming in 300 cross 300 or like 1,000 cross 1,000. So to do that, we need to again put the convolution layer to again shorten it down. But this time, the filter size, we can choose 5 cross 5, but the depth should be same as the input image. So since now the depth is 6, we have to choose it like 5 cross 5 cross 6 filters. And it is a common practice to increase the number of filters as we go right of the as you go further in the network. Okay.
Yes.
And yeah, so so since that's why we'll use 10 filters of size 5 × 5 × 6, and in the same operation we'll get another image of 24 × 24 × 10, and 10 is the depth. And if you see, the size of the image in the length and breadth wise is decreasing, and the size of the image, the depth wise, it is increasing. So if you do that, and uh, we'll get to a point where the image will be so small that we can use fully convolutional layer there, and it will, since it is small, it will, and also it is small, and also it has all the properties of the bigger image.
But with the every passing convolution layer, the image is not getting that small. I mean, there is a reduction of just in the size of, say, from 32 to 24 after using, say, convolution twice. So if I want to reduce an image, say, from 1000 to 1000 to some manageable size, say, of the size, say, 100 into 100, then I'll have to use a lot many convolution layers, isn't it? And those many parameters need to be learned by the network. So, I mean, how this process has an edge over the traditional ANN process then?
No, like, I mean, we have other layers as well. I will discuss, like, it will just drastically decrease the values with
Okay.
time. I mean,
Okay.
and if you see, even if you use convolution, if we can just increase the filter size a bit, like 7 × 7 or like 9 × 9, it will decrease drastically. So yeah, we'll discuss that later. I mean,
What is the yes, please continue.
yeah, so the thing is that if you count the number of parameters in ANN for this image, and, like, 10 CNN layers, even if with this speed, like 5 × 5 is reducing by, like, 4, you can see that there's a huge difference between them. It's like it will be in thousands, and the other one will be in millions. So I can show you, like, if I just yeah, I'll see.
What is the common size of a filter? I mean, which size of the filter we commonly use?
Sorry.
So what is the usual size of filter we use in
Yeah.
making?
Okay. So there is 1 × 1 as well, which we use for a special purpose, but I don't think I'm going to discuss that today. But the common size is 3 × 3 and 5 × 5, and sometimes 7 × 7. So
Okay.
yeah, it's a combination of that. So actually, if I say, if I have to classify a cat and dog today, I'll not be sitting around and designing this channels. From 2013 to 2018, I guess, or 20, or till today, people have developed, like, numerous CNN architectures, and they have so these people at Google and Microsoft, and not Microsoft, I guess, just Google, and all these good big universities, they have much larger computers than that we have. So what they do is that they just they have made huge networks, like a 50 or 100, 150 size, and they have trained that, and they have experimented and found that, okay, this architecture works good. So for, like, if you do a image classification task, and if it is just normal stuff, like, if you suppose, let's say, ISRO is doing image classification, that is the with the image that is coming from the space, there's sort of a new sort of kind of image. It is not the common image, or it's not not an image of the things that we see every day. So for that, we need to design a new CNN. But, like, for everyday things, like, we don't need to design a CNN. We can just pass it to any existing CNN that is there in the market. It's available free in the internet. We can just pass that to them, and we can just see this thing's output in a very short time. We don't need to worry about that. So the thing about, like, like, how to design, or like what layers to choose, what should we do. So those things, I mean, I generally don't encounter in my daily life. But if you work
Okay.
in a specialized, yeah,
So
case, it is.
how difficult it is to bring the existing frameworks into our own program? So like you mentioned that
Nothing.
there are frameworks available.
10 minutes.
Requires
Just
10 minutes
just
of time.
yeah, just like just take the code, like they have written, like, so there is a library that's called Torch Vision. If I'll show you, Torch Vision models. So you go models and pitch and width. So this is the code, I guess. Just one second. Yeah. So see, so what? So ResNet is a model, like one of the good models. It's discussed in 2015, but it's still a good model. People use it as a benchmark. So from torchvision.models, you import ResNet 50 and ResNet 50 weights. Okay. So you created the model ResNet 50 with the weights. So what happens is that when you start training a neural network, you have to initialize the model with random weights. Then the model will learn, and after learning all these things, the weight that it got at the final iteration will the final weight, which will be the optimal weights. So without training anything, you can just get that weights, like no ResNet 50 weights dot ImageNet 1 kp1. So all these weights are created according to this ImageNet dataset, which is a dataset of 1,000 images of common everyday things and everyday animals, or like vehicles that we see. So there are thousands of them. So it's trained on that. So it's believed that since it is trained on all these basic things that we see every day, uh, it has captured all the patterns and all the curves and edges and everything that we can see that we can encounter in our daily life. So it's a better way to use this model as our base model. And yeah,
Okay.
so
So when we import this ResNet or any other existing framework, so when we import this, what is being actually imported? So
uh,
if these pre-trained weights are being imported, then I mean, in which form this existing framework is available for us within the program to explore? I mean, will these weights be available in the form of a grid or what? In what form these pre-trained weights are available?
yeah, this weights, like if you just want the weights, not the model, because see, if you have the weights, you have to feed it to a model, right? It's not like that you can just take the weights, because like so there is two things, like there is model and its associated weights. Okay. So
Mhm.
talking about model, um, if you just take the model and initialize it, you'll get random weights. But if you say that, okay, this is my model, but use these weights, okay, like here, if you see ResNet and weights equal to this one, like you're saying that use this weights, it will use that weight as its weight. So if you just want to get the weights, it will just be a dictionary of weights, like it will say that there's a layer one weight, there's layer two weight, layer three weight, like that.
Oh, okay. So, like in the second option, only the structure of the framework shall get imported without any weights. So, like in the second option, wherein in the comments it is given that using no weights. So, I suppose that
Yeah,
all
yeah, 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 yeah.
the structure of the framework, like these many CNN layers are there, or these many max pool layers are there. Although,
Yeah,
I
yeah,
mean,
yeah.
the skeleton will get imported. Is this
Yes. I
so?
mean,
So now say if I want to recognize my image and which is not there in the ResNet, so how will I recognize a new image which is not the part of the ResNet framework?
see, like, if you want to recognize your cat as cat, so
Yeah.
you can just use the ImageNet weights there, right there in the first line, because they have cats in the ImageNet. Let's say we're recognizing liver cancer. You have like 5 types of liver cancer, and we want to train, we want a model to do that. But if you use these weights, it will not happen, because these are the weights that is trained for general images. So for that, what you need to do is that, so what you can do is that you can create your own CNN like this. Take CNN and then create filters and everything. Or what you can do is that you can just take this less than 50, which is a good model in the computer vision, and then you do not import the weights. You just take the model as it is, and the weights would be randomly initialized, and then you train your rest 50 with the image that you have with you, like the liver cancer images, and with the specific class. And after you do that, you then have your model and have your weights with you. Now the model will be borrowed, but the weights are not.
Okay. Clear. Yeah. Thanks.
Okay, good. Okay, so we've done that. Yeah, before going here, like I just want to discuss. So I said here, like, you can borrow image, or you can you can borrow the model, or you can borrow the model and the weight. So what about borrowing the model and borrowing half of the weight? Okay, so
Yes.
it's believed that so when you like train a model, the initial layers of the model will learn the very generic features such as curves, uh, uh, edges, and sharp edges, horizontal edges, vertical edges, which is there in every image that you see in this real world. Like if you say the astronomical images or medical images, they have curves and lines. Okay, but when you go further in the network, in the down the line, you will see uh, much finer structures getting identified by the network, like cat face or like eyes or something that is related to those images. Okay, so what people have done is that they have said, okay, we'll take the weights, take the trend weights. Okay, and what we'll do is that for the last 3 or 4 layers, we will sort of so every weights except the last 4 layers will be freezed. That means that will not be trend. It will be fixed. So it will be fixed and it will not be trend. So that is done by saying gradients equals to false. So if you set the gradient equal to false, there will be no gradient computed correspond to that weights. So there is way to there is one way, like when you freeze the weights of the initial, let's say 10 or 15 layers, or you just don't freeze the last n layers, like 2, 3, or 4 layers. So those 3, 4 layers have learned specific structure of that data, so they are specific to that data. So that's why you just don't fix that, you just fix the first half, and when you are learning, you're just updating the weights in those last 3, 4 layers. And since the number of class is now changed, like here you have like 1,000 class, but in ImageNet, but now let's say we are doing this liver cancer, which is just five class. You just have to change the final layer from 1,000 to 5 and unfreeze those last n layers. And when you train the model, it will get trends faster, because let's say like you have frozen 80% of the weight and you're just training with the 20%, and 20% of the weight is much smaller than the 80%, and you're just training this 20%, it will be 5 times faster, and it will not need it will not to learn these basic structures that is there in the image. It is already learned. It will just learn the specific feature. And this type of learning is called transfer learning, where the knowledge of a model learned from one dataset is getting transferred to the other dataset.
Okay. Yeah, clear.
Yeah. So if you just go to this PyTorch torch vision, you can see the example of transfer learning. Like there's a lot, like they have all these weights and the average accuracy and all these weights are free.
So like here the parameters are given in millions, I guess 7.4 M. So here M indicates the
yeah.
million.
A million. But like,
Okay.
if you just used, so it's like the ImageNet image is much larger than the image that we see here in this slide. It's like 300 cross 400 or something. So it's much larger. And if you do the FCNN for that, so sorry, not FCNN, like the fully connected neural network, FCNN. Yeah, I mean, not convolutional, there's the NN. So the parameter will go in billion. And if you have a like, MacBook or something, MacBook or like, if you have just a gaming laptop, that can handle 6 million or like, this 80 million parameters. So it's not that big. I mean, it seems big, but it's not that big. So, but now the transformer models, the chat GPT models, the GPT models, they have parameters in billions. So in terms of that, there's nothing. So like, if it is less than 100 million, yeah, if it is less than 100 million, it's fine. It can be trained on your laptop.
Oh, I see. So all source to the parameters which are up to the level of 100 million. So for them, I can use my own laptop and no high-end
No,
machine like
it's not, no, it's not like that. I mean, of course, like your laptop will take longer time. Like if I just use a high-end GPU for that, V100 or A100, it can be done in like, one epoch will take like 2 or 3 minutes. But if you do the same thing in your laptop, it will take half an hour. Okay. But what I'm saying is that it will not freeze. Okay. Like ResNet, you can train in your laptop. It's fine. But it's better like if you have a better GPU.
Okay.
It will not get hanged, what I'm saying. 100 million,
Yes.
I don't think, like for MacBook, it's fine. I'm not sure about the Windows system. But yeah, like it's not that big. So this ResNet I trained, I guess, they have smaller parameters there. And if you have a like Colab, Google Colab, you can train all this model in Google Colab. It's free and it's fast, and it can handle all these models. And since we are like doing the transfer learning, yeah, so you're doing transfer learning now, so you don't need all these parameters, right? You can just use 20% of it. If it is 20 million, you'll be using only 4 million. Okay, so
Yes.
all the other things will be freezed, so it will be much faster.
Yes. And will we be studying transfer learning in this course, or will you be taking one demo of the transfer learning in one of the problem solving session?
Yeah, let me see, like if you request that, I can do that. Let me see, like what is the content in week 5. So in week 5, if you go to evolution of CNN architecture, part 1 and part 2, here I guess Professor has discussed all those architecture that is proposed from 2013 till 2018 or something. So the recent CNN architectures, fine-tuning CNN. So fine-tuning CNN is the transfer learning stuff. Let me see the lecture material. It will be more clear there. Week 5, right?
Yes.
You fine-tuning CNN. Yeah, see, this is the thing I was telling. Low-level features like edges and all, mid-level features and high-level features. Okay, so transfer learning, what we do is that we transfer this knowledge. So we have the knowledge of the source task, then you transfer it to the target task. And yeah, you see, so there's this input, then feature extraction layer, which are the initial layers. We do that, we freeze those, and we just randomly initialize the classification layers or the end layers, which are, like, so we can say here that initial layers are the feature extraction layers, which are just extracting essential features, and end layers are like the high level layer, high level feature layer, where we sort of find those features which are essential to classify between all these cats, dogs, and ships. So they're not generic; they're specific to a class. So that's why, like, That's why like we use this reuse this knowledge there. And yeah, so this is the thing that he discussed. And let me see like, if I can get a notebook or something where we can discuss about how to do that hands-on, or you can just do it in the next session if you want. Okay, so just continue. Yeah. So yeah, so this is that. And one problem that happened with this method that I'll just discuss. Give me 1 second. Okay, so what the problem that happened is that let's say like um, um, okay, so um, this is the first block that we're trying here. Okay, and if you see this animation here, so it's just moving one block to the right and one block to the down. Okay, so what if we do not want that? What if we just jump 2 blocks to the right and 3 blocks to the down, or like 2 blocks to the down? Okay, so the number of jump that we're taking while we're like parsing the image is called stride. So if we're just doing one jump, it is called stride of 1. If we do 2 jump, it is called the stride of 2. Okay, and if you want to reduce the size of image very fast, you can increase the stride as well. Like if I just jump from here to here and then here, so the resultant image will be 3x3. You see, and if I just jump 1 block at a time, it will be 1, 2, 3, 1, 2, 3, 4, 5. The image will be 5x5. Okay, so yeah, so it is written here. If the stride is 1, so the output size is calculated using this formula: n minus f by stride entire plus 1. N is the size of the image, f is the size of the filter. So n is 7 and f is 3. 7 minus 3 is 4 by the stride is 1, it is just 1 plus 1. So 4 plus 1 is 5. If the stride is 2, it is by 2 plus 1, it is 3. If the stride is 3, it is 7 minus 3 is 4 by 3 is like 1 point something, and then plus 1 is 2 point something. So the stride is 3, we're not getting a whole number. Okay, so we're not getting a real image. So how to solve this problem? So we can solve this problem by zero padding. So what we did is that we added zeros across this image. Okay. Yeah. So okay. So what I did is that we're at zero padding. So now, and also one more problem that is not written in the slide is that if you see this pixel, it is getting involved in this computation and in this computation, and if you go down in this computation and in this computation as well. So one pixel is getting involved in 4 computations. So when you're reducing the image to a smaller value, we ensure that this smaller image, even if it is smaller, it is capturing all the things that is there in the bigger image. So if you see for this pixel or this pixel in general, they have a larger contribution to the final image than this pixel that is there and lying in the corner, like here or here. So if you just see this pixel, the second pixel on the top left corner, so it is getting involved here and in the second time. Then after that, it is not getting involved anywhere. Like then you just jump a cell down, so it is not getting involved again. And like if you see this corner piece, it is getting involved once in its entire lifetime. So what we do is that we said that we can just add a border of zeros across this image, so that it will, so the zero is correspond to the color of white, so it will give a white patch across the image, but it will not have any values because we don't care what zero is contributing, but this little pixel will be involved more. So now since it is zero, this filter will cover this 4 times, like for this, for this, for this, and for this. So now everyone gets an equal chance to getting involved in the convolution operation. But it has a downside is that if we increase the size of the image, we sort of need to again think about how to reduce it, because and we're not increasing by much dimension, just 1 or 2 layers is added. So so there's that. Uh, uh, so so that has a downside, but we generally use zero padding to sort of getting the corner and the border pixels more involved in the computation. So this is a cheat sheet. So I'll just summarize the conflict that we have. So let's say we have an image of volume of size W cross H cross G. That is like width cross height cross the depth. So we need 4 hyperparameters. That is like number of filters that we need, and their spatial extent F, and the stride, and the amount of zero padding. Okay, and so the F is the filter size, that is like n cross n or something. So but we can just say F cross F. So filters are generally square because images are generally square. I mean, we just pre-process the image to be square, and we can do a rectangle image and parse it through a square filter. That is fine, but people just do square image. We can do it with a rectangle image as well. And this is the number of filters, and this is the spatial extent. And we don't talk about the depth of the filter, because we know that the depth of the filter should be equal to the depth of the image, right? And with the stride, I mean the amount of times, the number of steps that the filter will take while moving around the image. And the fourth one is the amount of zero padding. So should you just add 1 layer of zero padding, or just 2 or 3 or 4? The maximum that I've seen so far is just 2. People would go beyond 2, like it is like creating an entire image out of it, like around the original image. So it's just 2, basically, for the 2. And and let's say the final image that we get has a size of W2 cross H2 cross D2. So the formula to calculate this W2 would be like, take the width of the original image, then subtract the filter size, then add 2 times the size of the padding, divided by the size of the stride, then whole plus 1. It's not a plus 1 on the stride, it's a whole plus 1. Similarly, x2 is that, and the width and height of the image, since the width and height of the image is generally same because of the square, they have the same formula for that. And the depth of the image will depend on the number of filters. So D2 is equal to K. So if you go here, you can see we had like 6 filter of 5 plus 5 plus 3. we had 6 layers. So here, so there are 6 convolutional filters. You get 6 in the depth. So since we're like using the same filter for the entire image, we're sort of traveling across the image. We call it the parameter sharing. Like here in this image, you can see that each pixel of the image has one parameter, but since we're like moving the stuff across the image, we're sort of, and this is the parameter, we're sort of sharing this parameter across all the pixels, and we call that parameter sharing. And with parameter sharing introduced, the number of weights per filter will be f cross d, where d is the depth, and the total a total of f cross d into number of uh, number of this what number of filters, and these are the number of weights that we have, and each filter will have a bias term with it. So k biases as well. So total like f cross t cross k plus k number of weights, number of parameters.
This calculation is not clear because whenever we convolve, so one bias is involved in one convolution, one bias is involved. So how can we have, say, k number of the biases here? So what this k here is? So are we convolving the image k number of the times here or not?
No. So each time you convolve with one filter, right?
Yes.
So this little thing, okay. So this 5x5x3 filter has one bias term. So
Correct.
if I place this filter here on top, you'll get a value. You add the bias to that. Then you shift right. You compute the dot product. You get a value. You add the same bias to that.
Correct. So whenever we convolve once, one bias is included. So if we are including k number of the bias, what does it mean? That are
we have k
convolving?
filters. We have k filters.
K is the number of the filters.
Filters, yeah. I mean, so now like we have 2 filters here. So each filter has this 5x5x3 weights plus one bias.
Plus one bias. But then, I mean, this will only convolve a particular portion of the image. And whereas to convolve the entire image, I mean, this needs to be what? Needs to be...
No. Why it is convolving 1% of the image? This is the filter, right? It will convolve the entire image.
Yes, so in that formula, when we wrote, say, the W transpose of X plus B, so what this B here refers to and what was W? W was 75 in that slide.
W is 75. X
yes.
is one part of image. If you change the X, I mean, X is the representing that smaller portion of the image.
Yes, and for every smaller portion of the image whose size is 75, one bias is involved. So because
yes.
if we move this filter, say, depending upon the number of the times we are moving this filter over the image, so those many biases.
No. One bias for that.
One bias for the entire operation?
Entire operation, like that's what I said. Like, you know, when you have like 5x5x3 filter, they have like 75 weights, and you multiply those weights to those filter pixels, you get one value. You add one bias, then you shift the same filter with the same weights. You're not changing the weights now. Since the weights are same, the bias that you will be adding after multiplying these weights to the pixel will also be same. That is like, you know, the same bias. So you get like 75 plus 1. I'm like
Yes.
76 parameters per per filter.
Yes.
Per filter.
Yeah. Clear. So can you go back to that slide and wherein that calculation was given here? This one. So we have F cross F. So it introduces, say, F. What is F here? So it was the size of the filter, like say 5 cross 5.
Yes.
Yes. So this is 5 cross 5 cross 3. D1 is 3 here. Weights per filter. 25, say this value comes out to be 75, and for a total of 75 multiplied by, say, if we are using 6 number of such filters, yes, it's true.
Yes.
Yeah, right.
If you just take k common, it will like f cross d plus 1 into k.
Yes.
So 75 plus 1 into 6.
Correct. Yeah, fine.
Yeah. Okay, great. So you have this number of weights. In the output volume, D is the depth. Yeah, I'm not sure like what is slash line represents, but yeah, we can just skip that. Okay, so that like summarizes the convolution operation. Then we have like this pooling operation. So the pooling operation is like 1 second. Yeah, this pooling operation. The pooling operation is a downsampling operation, and it is typically applied after the convolution. That I said, like you have con relu, then we had this con relu block, but actually what happened is that people introduced pooling. So now it's like con relu pull, con relu pull, con relu pull. So convolution layer is a step by step application of this con relu pull, and con relu pull until you get a small image. So it is typically applied at the convolution layer, which does the same spatial invariance as the convolution operation. In particular, it picks out the max or the average, among that small region. So if you can just see, there is 2 type of pooling. One is max pooling or the average pooling. It's very clear, I guess, like from the image itself. So what you do is that you just take a filter and you pick the max. Like it's not a trainable layer, it's not trainable layer. So it's just a function. Okay, what you do is that you take 4x4 size, you pick the maximum, then you shift right by 1, then you take another 4x4 chunk, then you pick the maximum out of that, and you get this reduced image. So what we're doing here is that we're sort of getting all the important values that is needed from an image without involving any parameters. That is one. Second, also drastically reducing the image size. If you see, it's 6x6 image getting half, like 3x3, just by taking the maximum values. And we can do the same thing with an average as well. If we don't want to do the maximum, we can just do the average value as well. So what this do is that this preserves the detected features, and max pooling is most commonly used in all the architectures that is designed after that 2013 and 2014. But average is was used in Linet. Linet was designed by Jan Lee Kuhn, who is one of the first one to design CNN in 1998. So they're using Linet, but not used very popularly nowadays. It just downsample the feature map by taking the averages. Okay. So the once you do all those things, we reduced all those images, we come to a point where the size of image is very small. Now what we can do, we can just flatten it. We can just take all this, image and flatten. Let's say the final image is 3x3. No dimension is involved. But generally, the dimension grows with time. That as I said here, the dimension grows with time. It had 3, it became 6, now it became 10. Now it is growing with time. So, but like for example, I'm just showing that here the dimension is 1. What you can do is that you can just take the 3 pixel, put it here, then take this 3, put it here, then take this 3, put it here. Now we have a small enough image to do that. because if you have a small enough image, you can just flatten it, and then we can just add a couple of fully connected layers, FC layers, till you are satisfied, and then at the end we can just attach the output layer.
But then there won't be a single this image after this pooling operation, because we used multiple number of the filters, resulting into the multiple number of the feature maps, and resulting into many max pooled images. So the number of, even though the size of the image is less, but then there would be many such images. So again, resulting into a pretty large value of this line, this input layer to the neural network.
No, like so if I add a max pool here, so the size of the depth will be 6 because it will be applied to each image individually. So let's say like if I applied one filter, I'm getting this one. I'll apply a max pool here, and I'll get a smaller image. Like if I get max pool of size 2x2, I'll be getting like 14x14x1. So next I'll be getting another 14x14x1. When I club that, it will be 6x14x14. And here, instead of 28x28x6, it will be 14x14x6. So it's sort of reducing the size, not increasing.
It's
And
true
if
that we are reducing. It's true that we are reducing the size, but then we would be having a pretty large value of
depth, right?
Yes.
Yeah. So if you see if you go to the conv layer, if you go to this models, if you just run any block, just after the session, just go and run, you see the end layer will have a channel of say like 50 or 60 or let's say 100, but the size of the image will be 5x5 or like 7x7, like that. So if it is 5x5, even if you have like a 100 say channels, what I can do like 100 into 5 into 5, that's like 2500. So 2500 neuron is not that much. So you'll have 2500 neurons here, then you can just reduce it to 1025, then the next layer like 500 something, then 200, then less than 100, and then the number of classes. Or if it is 2500 something, you can just directly attach the fully connected layer, the output layer, if the output size is 1000. See, if the output size is 1000 for the ImageNet, it is not very problematic if you have a pre-output layer of 2500 size, right? I mean 2500 to 100 is pretty much achievable. So yeah, so what I was trying to say is that yeah, it's achievable. So even if the depth is so much, the size of the image will be so small that if you extend it, it will be smaller. Just trust me on that. So it is smaller.
Yeah, so after this flattening, so basically we have lost here that spatial or the local neighborhood of the pixels which we were maintaining so far before this last layer. So
yeah,
so how to, I mean, but then here or that spatial thing has been lost when we create a single input layer from the multiple small images.
yeah, no. Like what happens is that you have this spatial relation in the pixel level. Now you have like come up a long way down, and we have like all these features that is extracted and that is kept in the small images. So if you have a image of MNIST, there is a handwritten digit data set where you just have this image of 7 and 6 or 0 to 9 basically. So if you just flatten that, so the size of the flattened layer will be 784. Okay, so because the image size is 28 plus 28 plus 1, if we just multiply that, 28 plus times 28 is 784. And if you turn ANN on that, it will give you 98% accuracy. That means 28 plus 28, and with that simple structure, is not very hard for the ANN to maintain the spatial accuracy. I mean, it's not like that ANN do not care about spatial accuracy. It learns spatial accuracy, but not efficiently as a CNN does. So once the image start getting complex, ANN cannot handle that. Okay, so you
Yeah.
still preserve the spatial relationship, but it is much simpler now. It is much smaller now. So anyone can handle that.
Okay.
Yeah. So and this is the last slide, I guess. Yeah. So a moment. Okay, great. So it's like the typical convolution neural network, where like this is the image of a car, and we have conv layer, we have ReLU layer, we have conv layer, ReLU layer, then full layer, and so like it's not like that after every conv value you should put a pull. We can just pull. We can just put after two layers, and doing that after like the image is reduced to small enough, we just pass it to the fully connected layer, and we get the output. Yeah, so that's it. Like this, that's all about the CNNs. Now we'll just see a bit about the coding that is involved with that. Yeah, so the transfer learning that I was talking about is now I'll see. Like I'll not go through the code in a very detailed way because it's too long, but I'll just give you the simple idea like what's happening in the code. So we'll first import all these files, all these functions.
So can we mix the code of scikit-learn with torch? Will it be allowed? Say, like here, instead of using the sampler of the torch, if I want to use sampler of say scikit-learn or the sampler of scipy, can I do that?
Yeah, you can do that. Like, but the output that you'll be getting from those libraries will be in NumPy. So the thing with PyTorch is that all those PyTorch, like all the PyTorch things, all the PyTorch models accept tensors. So tensor should be a torch tensor. You get that? Like the number that they're passing is still a floating point value, but it should be an object of a tensor class. So what you need to do is that you can just take those NumPy values and convert it to a PyTorch tensor just by typing this. So if you just like let's say you have a tensor numpy tensor value of A, what you can do is that you can just do torch dot tensor, something like that. You can just check the syntax. Now it will be a tensor. So you can just use these values now, like if we say a t, you can use if you know did sampling or something from scikit-learn and got A, you cannot directly work with A when you're working with scikit-learn, PyTorch, but you can definitely use AT, which is the same value, just different class, to do your thing. Yeah.
Okay. Yeah, I understand. Yeah, thanks.
Yeah. So and there are some of the helper functions that is there, loading the data, like normalizing and everything. So this the same for all the notebooks that you're gonna see. Just helper functions for evaluations. I'm just gonna run it. Helper function for training. So these are all helper functions. You need to worry about it. I just show you the basic idea that we are like looking for. Yeah. So yeah. So this like the transfer learning, which is 16 on Cypher 10. Cypher 10 is a dataset of like common images, common real world images of things and animals and like sheep, frog, cat, and dog, but like only 10 of them. It's like a saying a smaller version of ImageNet where we have real world images of thousands of class, and the total image number of images that we have in ImageNet is around 60 lakhs, I guess, something around that. But in Cypher 10, we just have 50,000, 60,000. So yeah, like that. Yeah, so we set all these values. So it is random seed. Random seed is set to to generate the same random values again and again, because when it trains something, we want the same random values to generate again and again when we want to compare it against the previous run. And the batch size is 256. That means how many images that we are trying to process in each time. Then number of epochs is 5, which means that we need to train the same with all the data set for 5 times. And the device is like, if it is GPU or CPU. So we have set it to GPU. So if there is a GPU is available, it will be set to the GPU. If it is not available, just set to CPU. Then we set the random seed. Then we load the data set of Cypher 10. So just download. Yeah. You can see the image batch is size of 256, 3 cross 64 cross 64. The image size is 64 cross 64, and the number of channel is 3, and the batch size is 256. And the labels are like 474626970. It doesn't mean anything, but each level is corresponding to a class, like cat or dog or like sheep or something like that. Then we will be loading the pre-trained model. So if you just recall, I just had like .vision.models.bgg16, and we're like doing pre-trained equals to true. If you just go here and see, pre-trained equals to true is deprecated. That means we're not using that anymore. But since there is an old notebook that has this pre-trained equals to true, deprecated means that that feature is not available in the library now, but you can use that and it will be removed in the subsequent iteration of the library. So if you are using the older version of the library, you can still use that. If you are using a new version, you cannot use that. So, and it is printing the model down below. I'll just see if it's working fine. Yeah, it is working fine because it's not that old. Yeah. And now you can see now you have the model of which is 16, which is a good CNN model, proposed by Google. No, it's not Google. So there is a visual geometry group, that is VGG, in Oxford. So they proposed this architecture in 2015, and this architecture like conv pull, then conv pull, then conv pull, and like all like all like that. They are like 37 layers, 30 convolution layers, and this seven uh, um, um, linear like fully connected layers. If
Okay,
you see
so
the filter size,
can I use some history kind of the thing here like we used to use in Keras to show the structure of the model, or is there a way to if I use, I mean, is there a way to
print
uh,
the model, right?
yes, correct.
Yeah, I mean, I don't think like there's any visual model printing tool that is associated with Torch, but you can uh, definitely use some third-party library like plotting PyTorch model. Let me see if it is PyTorch. Yeah, there is Torch Viz actually. So I remember the Torch Viz is there. You can just pass your model to Torch Viz and it'll give you this sort of um, um,
Okay.
visual. So Torch Viz, just remember that. Yeah, so we have this model now. So what we can do is that we need to like, so as I said, we need to unfreeze the last 1-2 layers and freeze everything else. So what we do is that first we freeze everything. So for parameters in model.parameters, so like we're passing through parameters in each layer, and we're just setting the required grads to false. Like, it will not compute the gradient. If it is not compute the gradient, it will not update the weights. So we did that. That is done. Then assume that we want to fine tune the last 2 layers. Okay. So last 3 layers. So we only set those layers requires grad to true. So we set everything as false. When you load a model, it will be already in true mode. So we did false. Then we just did those two, like last 3 layers as true. So we did that. For the last layer, since we are classifying number of the number of class in this data set is 10, and the model that we had has a data set of 1,000, we just change the number of classes here. So if you just see here, it has like in feature 4096, out feature 1,000, because this model is trained on the ImageNet, which has 1,000 class. What we did is that we just went to model.classifier. So this is the classifier block. So if you just go model dot features, you'll see all these things. If you do model dot classifier, you'll see all these things. So it is this model dot classifier dot 6. Now this is changed to linear, where the in feature is 904096 and the out feature is 10. Here,
So
see,
what's the
10.
meaning of these classifiers ranging from 0 to 6? Are we using how many layers are we using after flattening everything? So that we are using 7 classifiers
6.
here
Yes,
from
7.
0
Yeah.
to 7, 0 to 6, yeah. So linear, and then railway is fine. So but then why are we using rail? Okay, so these are not the classifiers. I think that these are here. The dropout is also there, and then we are using linear railroad dropout. I mean, two repetition of these. Linear ReLU and dropout twice, and then
Yes.
finally using linear. I see. Okay.
Yeah.
Fine. Clear, understanding.
Yeah. Now training. So now the model is set. Now we said that, so if you had a model from scratch, we would have learned all the words are exposed. Now we have a model where only some of the words are exposed. So we just take the model and the training process is same as the normal ANN stuff. So we define the model, we send the model to the device where it is GPU now, and we created the optimizer, we created the scheduler, like it's just normal ML training stuff. So train model is the function that we defined earlier. Plot training log is just calling the helper functions, showing and plotting the accuracy. If I just run that, it will train the model in some minute. And let's say it is getting trained. So I don't know why I hit train, because it will gonna take many time. It's gonna fit.
So it is going to be trained on how many classifiers? On the classifier, I mean it would be computing the gradient for the classifier
Last 3
one,
layers.
last 3. Okay.
You can change it.
Some error is there.
Yeah. Is the code provided by this course people? So I'm not sure like what is the error, but if you just go and see what's the output there.
So probably something need to be executed and which has not been executed. Quite possible, because here we started executing after a point of after a particular cells. So
Maybe
because of that.
maybe then I can just try again, but I don't think like we're gonna finish the execution within time, because training will take a lot of time. So I just show you the results like here itself.
Do we have access to this GitHub repo?
Yeah, it is public. I can give you the link.
Okay.
Yeah. This is the training loss. It is the total training time is 10 minutes only. See, it's only 10 minutes.
Yes.
And it is reduced, and it is the training accuracy that is getting increased. And now, like we had this number, we just assign these classes to this number. Like 0 is airplane, 1 is automobile, 2 is bird, 3 is cat, 4 is deer. And so you can see like by plotting how good is the model is. Like the actual is cat, but predicted SIP. It is SIP, predicted SIP. Most of them are predicted like correctly. But like if you want to improve the result, you can just unfreeze more layers to allow them to learn better representation.
So I have used some keras. I have done some tutorials in which the keras was used, but I'm totally new to Torch. So how difficult it is to learn Torch, if you know something about keras?
Yeah, keras is like more straightforward. Like it doesn't have like all the details that Torch has. So if you like doing the back propagation, weight updation, and all these things is inside the keras fit function. But here you just have to write it one by one. So that like it gives you more control over the code, which part you want to update, which part you don't want to update, all these things. But like Keras is more a out of the box thing which you can use for your task. Like if you have a very generic task, if the task is very difficult, like you just need to tune a lot, or like do a specific task, a specific thing, you cannot use Keras, I guess. You just have to go for Torch. But I can say that Torch and TensorFlow is now merged. So I can say that like when I was working in an industry, so industry people generally prefer TensorFlow because they have this integration with the Google Cloud and everything, and the visualization tool and everything. But if you come to research, so I'm doing the research now. So in the research, we prefer Torch because it has a lot of flexibility over TensorFlow, and you can do things that are like many different way in Torch than TensorFlow.
Okay.
Okay,
So
right.
if I start learning torts, then do I need to learn TensorFlow also after some time, because the TensorFlow is said to be more prominent thing.
In industry, yeah. But like, so what I do is that, like, I don't learn any coding thing. So you know that there is ChatGPT, right? So what I can do is that you
Yes.
can just take this Keras code and say that, okay, just write the PyTorch code that for me. So see, I mean, it's not very intelligent thing to do to learn a system like a language, because PyTorch might be obsolete in next 5 years. Okay, so what we as humans are giving the computer is that the ability to do the computation. So we need to think like, I mean, so we can say that, okay, you do the calculation, but we as a human has to give what to compute. It's not like that. We're giving the random thing. So if you just want to, if you just if you're clear in mind that, okay, I'll freeze the last four layers, then I'll train that. So you are clear in that, and you know that it will work. It doesn't matter what programming language that you're using, or like what library that you're using. So if you, let's say, if you just want to have to use Python, but you don't have a working knowledge of Python, you just go to ChatGPT. Like I would prefer that, go to ChatGPT and say, I have this problem in hand. Just give me a Python code. And if you just have a basic knowledge of Python, you can understand that and you can work with that. So it works, like, for me, because it's just you know what to do, but you don't know how to do that. And in real life, you have access to computers, internet. So if I don't use that to get your answers, so
Yes,
I
yes,
just use
yes,
in that way. I
yes,
mean,
yes.
if I don't get anything, I just ask ChatGPT, okay, what is the decision syntax for that? How do we do that? Because I know what to do. I don't want to waste my time learning that, okay, this is the way to do that. And after 3 or 4 years, they will say that, okay, this feature is obsolete now. We're launching new feature, new library. But what will I do now next? Like, learn that library as well. So it'll, like, all life learning libraries.
Yes, yes.
Okay. Actually, like, I'm not in India, so I'm currently in Australia. The time is like 10:30 now, so at
Oh,
night.
okay.
So
Yeah,
yeah,
yeah.
so we'll close the session for today.
Yeah.
We'll meet
Yes.
next week, and I guess next week is on Tuesday. I have a session. So
So
yeah,
yeah, this session was very useful. So from where can I get the schedule of these problem solving sessions?
so if you go to the announcement section here, announcement. So they have a session, like section. So there are like 4 students. They're sort of now teaching now. I have this one, this case Wednesday session.
Saturday session.
No, I had Monday. Say I had Tuesday, but I had to do some like I had a thing, so I couldn't do that. So I just shifted it to Saturday. But next Tuesday I'll be doing from 6 to 10. So I'll try to balance 6 to 8. So say 6 to 8, not 6 to 10. Like do the time scheduling a bit, because 6 to 8 is like here 10:30 p.m. to 12:30 p.m. 12:30 a.m. in the night. So it's getting
Okay.
late, like for me. In one
Ah.
session, I slept after like one or 1.5 years, 5 hours. So like I was so tired. And people here in Australia, like they prefer that they sleep early. After 7 p.m., there will be no one in the road. After 9, it is
Mhm.
like blank. So everyone just sleep at 10, 9, 10. It is quiet, and everyone just wake up at 5 to 6. So is there a thing? So it's very hard to stay awake till 12:30 or 1 at night if you're not watching a movie.
Yes, yes.
Yeah.
Thank you so
Okay,
much. And it was a very, very useful session. Thanks.
thank you. I will be uploading the session to the YouTube, and if you want to refer back to the session, you can do that. You actually can find. I mean, those people will share. Then tell people will share. People will share the YouTube link. But I'm just sharing the notebook link in the chat now. You can have a look, and
Yeah,
we'll meet next week. You just take
sure.
the link from the chat. I'll just close the session. You won't be able to access the chat. Okay, I'm closing the session. Thank you.
Yeah, thank you so much.